Okay, I'd like to look at an overview of everything that I've talked about for these elastic collisions in 2 dimensions. It was already a pretty high-level discussion because we've already done everything in the class, but I'd like to do this just everything on one slide so that you have one sort of reference that you can use later on when you need to use it while you're programming your final projects, while you're programming your mini projects, while you're programming even the stuff in class, although I'll be there with you in class, so I don't think you're going to really need this. But I'd like to have this available to you, everything for this in one situation, so you can try to use it the way you think best in your particular situation. So these are the 6 steps, the 5 steps really. First, you have to know what it is you're dealing with in your object, right? So what do you need to have in your simulation for you to use these things? You need to have 2 balls at least. You can have 7, you can have 2,000. It doesn't really matter as long as you have 2 ball objects in your program. Each of those is going to need a mass, a radius, a position, and a velocity. I've gone ahead and said the mass and radius are constants. If you have a really complicated final project, you might do something where you're changing the mass or you're changing the radius. And in those cases, they're not constants over the entire simulation, but they still should be constants, hopefully, over the time of a collision, because our collisions we imagine to be instantaneous, even over our 30 millisecond time frame for updating our simulation, 30, 35 milliseconds, whatever it actually happens to be. I think the average is about 34 milliseconds. But everything that we've done uses a variable time, so we don't have to worry about what the actual time step is. We can deal with Microsoft taking over the computer for a few milliseconds, and everything should still look like it's running smoothly. So we've got all these things that should happen, and all these things that should stay constant, the mass and the radius of each ball. So that's 2 to the n constants. These are all stored in the object, so you don't have to really remember how many there are. We have these variable properties as well, and they're going to be more important for our simulation. We're going to need the mass and the radius, but the variable properties are the things we're going to have to check and the things we're going to have to change. The first one is the position. The position is only going to change during the update, but it's going to be important to detect in step 1 what happens in the collision, when the collision occurs with the collision detection. And then the velocity, steps 3 to 5 are going to use the velocity exclusively. The only thing about the position that they're going to worry about is the result of step 2, which is the geometry of finding the normal directions. So steps 1 and 2 use the position. Step 1, like I said, is detecting the collision. Detecting the collision you've done over and over and over again. It's just check this distance, the magnitude of the displacement between the 2 balls, and if that's less than R1 plus R2, then you have this interpenetration region, which is no good because 2 things can't be in the same place at the same time. That's sort of what we do in the real world, is we have solid objects that don't ever interpenetrate. That's just the way the world works. If you don't like that, you can take it up with whoever designed the world. But I don't have anything to do with that, and if you're trying to simulate the world, you don't want to have that happen unless you're dealing with ghosts or something like that in a game. So to avoid that, as soon as we detect that, so we check every step to see if that's happened, as x1 and x2 are changing, we check this detection, or this collision detector. We use this comparison every single time we run the engine, and when we find this, then we go and do steps 2 to 5. Step 2 is sort of a bridge. It's something you do once during each collision, and it's still geometrical, right? This is the last real geometrical step that we do. Everything else has to do with vector algebra and vector geometry instead of sort of geometry. So we're sort of translating the geometry into into vector algebra, just the way you're going to take all this vector algebra and turn it into a program, right? So first we have to find the collision directions, right? The collisions are along this line here, are somewhere between this line between the two centers. And so we want to use that line because that's where all the action happens. That's where the impulse happens, and the impulse is where the force happens, right? Because it's an elastic collision. If it was inelastic, we might have to take care of some things that happen in the tangential direction. We do that in our force step, not in our collision detector or collision step. So that would still work. That we have a way to make that all work out, but we wouldn't use the collision detector for that. So finding this normal direction is fairly simple. You just take the displacement and divide it by the distance being the magnitude of the displacement, the thing that we just used above there. The displacement is a vector, and I have the components written out here in step 2 for that vector, right? Just components of the normal direction are the components of the displacement divided each one by the distance. So the components of the displacement are just the displacement in the x direction and the displacement in the y direction. Divide that by the total distance between the two objects, and you're going to have a unitary vector. You'll have a unit vector, a vector with magnitude 1 and no units. And that's one of the directions that we need. That's the direction where all the action happens. The other direction is the one where none of the action happens. And what we can use that for is minus that's the tangential direction. The x component of the tangential direction is minus the y component of the normal direction, at least the way I've drawn it here, and the y component of the tangential direction is the x component of the normal direction. Again, as I've drawn it here. I could do some fancy vector math, but it's really actually a three-dimensional vector math that I'd have to use, so I'm avoiding it, even though we might get to it in Unit 5 rather, but in Unit 3 it's a little bit too much for us right now. Excuse me. So after we find those, then we can do everything that's all native to the actual collision. Okay, and the first thing we want to do is we want to just break up the initial velocity into these components, the normal and tangential components, right, of the velocity. So we're keeping track of the velocity, we're keeping track of the position both in the x and xy coordinate system. The coordinate system that lets us do the least amount of computation and introduce the fewest errors is going to be the coordinate system that is based around the normal and the tangential directions. Remember, the whole reason why we use vectors is because vectors have a representation in each basis, right? The normal tangential basis or the xy basis, but they'll always have the same magnitude, for example. So we can rotate our, as long as we understand how to rotate our coordinate system, we can rotate our vector similarly, and we have the same vector. If we rotate the coordinate system, do all the mathematics, do all the physics stuff, rotate it back, everything will be the same as if we did everything in that original coordinate system. But sometimes it's just easier to use a coordinate system particular to a situation. In this case, each collision between a billiard ball and another billiard ball will have its own coordinate system, its own normal and tangential direction. And so to find these coordinates, we just look at the projection. Right? And the projection of a vector is the dot product of that vector times the unit vector in the direction of the projection. All right, which is a fancy way of saying you take, for example, for the normal direction, the vector component in the normal direction is equal to the x component of the vector in times the x component of the unit normal vector, plus the y component of the vector times the y component of the unit normal. So that's just your dot product. It's the sum, and your dot product is the sum of the products of the components in the individual directions. That's what I've written down here. And here, like I said, I've written it down for all four cases: the two in the normal direction, which will give us the things that we're going to change, and the two in the tangential direction, which will give us the things that we'll keep and bring back later in step 5, but ignore in step 4 because they're not going to change over the course of the calculation. What we're going to do is change in step 4 the normal component. Now, I've written down the complicated form here. You'll remember from lecture 2 that there was a simpler form, or part 2 of this lecture. There was a simpler form. I have the more complicated form here. This is the same formula that you'd get for a dead-on collision in one dimension. I guess they're all dead-on collisions in one dimension. But this is the same formula you'd get in a one-dimensional collision. So we've looked at that before. We've derived it already. It's fairly simple compared to, say, aberration equations or something like that for optics. But basically, that just says that you have some sort of weighted average of the two velocities the velocities of the two balls is what I mean, is going to be the new velocity of each ball. And those actual signs and the orders and all that depends on each ball. The main idea is that if they're both equal, you get the simplified case. If both of the balls have the same masses, that is, you have the simplified case where the velocities just flip. So the new normal component of the first ball would be the old normal component of the second ball, and vice versa. The new normal component of the second ball would be the old normal component of the first ball. Same thing for each one, just be consistent about everything. That's the reason why the M1 and M2 are flipped here, is because you have to be consistent about everything so you get the right signs. Fairly simple. Then you just recombine everything. Everything will be great after you recombine it. And you do that by treating these components that you found in 3 and 4 as vectors. How do you treat them as vectors? You multiply them by the unit vector in the direction they're supposed to be pointing in, right? So you find the tangential velocity by taking the tangential speed, v1t, multiplying it by the unit tangent, right? And do the same thing for the unit normal, right? You take the new velocity in the normal direction for part 1 and you multiply it by the unit normal. And in this case, basically what you end up doing is you have a bunch of the x components. You have the x components of these two things added together, and after being scaled by the velocities of the tangential and the normal direction. It's very, very simple. I've done it for both of these things. You just have to figure out how to program it in. And really, this is about as direct as I've ever seen for taking a bunch of mathematics and putting it into a program. So it's going to be very, very easy for you to do this after you've been programming for a little while. Might be a little difficult right now. You're still in this phase of learning how to translate mathematics into a computer program. It's not, I mean, it seems pretty natural after a little while, but at the beginning you have two different sets of symbols that maybe you're not completely familiar with and some special rules in the programming situation. So, I mean, don't let that get you down. You just have to do it over and over and over again. You might do some programming practice runs if you're having trouble with this. Take some simple equations from your physics book and just figure out how to program them in, and everything will be hunky-dory after you've made those simple functions for yourself, like translating temperatures from Celsius to Fahrenheit or calculating densities. All right, so I think this is about as much time as this software is going to give me. Thank you very much for listening, and I'll see you in class.